In the annals of scientific exploration, few quests have been as persistent and as elusive as the search for a unified theory. This grand theory of everything is the holy grail of physics, a single mathematical framework capable of describing all of nature's forces. Albert Einstein, the man who unified space and time in his special and general theories of relativity, dedicated more than 3 decades of his life to this pursuit. Despite his unparalleled genius, he never tasted success. Fast forward to the present day and the quest continues. Scientists are striving to marry two seemingly incompatible theories: general relativity, which describes the universe on a grand scale, encompassing stars and galaxies, and quantum mechanics, which takes us into the bizarre world of subatomic particles. Individually, each theory is remarkably successful, but when they are combined, like in the dense center of a black hole, the mathematics simply falls apart. In the 1970s, the solution appeared to emerge from an unlikely place. Physicists, grappling to understand the strong nuclear force that holds the atomic nucleus together, stumbled upon an equation that hinted at vibrating strings as the fundamental constituents of matter. But this promising lead soon seemed redundant when a different theory provided the answer to the nuclear puzzle. Almost everyone abandoned string theory, leaving only a small group of diehards who, captivated by the elegance of its mathematics, continued to explore its potential. Among these were Schwartz and his colleague Joel Scherk. They saw in string theory not a description of nuclear forces, but a quantum theory of gravity. This was a game-changing realization. They proposed that the failed theory of the strong nuclear force was, in fact, the solution to one of the greatest challenges in physics, uniting gravity and quantum mechanics. But their revolutionary idea fell on deaf ears. The scientific community simply wasn't ready. Undeterred, Schwartz and a new convert, Michael Green, spent years developing string theory in relative isolation. Finally, in 1984, they achieved a breakthrough. They showed that string theory, with its beautiful mathematics, could sidestep potential pitfalls that had been considered fatal. This time, their voices were heard. In the corridors of Princeton University and the Institute for Advanced Study, almost half the world's experts in related fields were now listening. This marked a turning point, not just in the journey of string theory, but in our understanding of the fundamental nature of the universe. As we stand on the precipice of a new era in physics, it is clear that a new paradigm of space and time is needed. We've come a long way since Einstein's days, but the unified theory remains just out of reach. Yet the story of string theory is a testament to the power of tenacity and the allure of beautiful mathematics. It's a journey that's far from over, and its implications for the world of physics are profound. String theory is based on the one-dimensional vibration of strings. However, the vibration of the strings require 6 more dimensions to vibrate than the 4 we observe, 1 of time and 3 of space. This requirement for 6 more than the observed dimensions is contrary to a proven theory of dimensions called the Bott periodicity theorem, which shows that there can be no more than the 1 plus 3 dimensions as observed because extra dimensions will roll up into one another, like a set of Russian dolls, where a larger one contains a smaller copy inside it. The new approach avoids this dilemma altogether by assuming that the vibrations of the theory are not the one-dimensional vibrations of strings, but the 3-dimensional vibrations in one of the 2 reciprocal aspects of scalar motion. As they say, this changes everything. Stay tuned for more, much more, as we explore the impact of this new approach to fundamental physics in future videos.